Okay, so a check of understanding on working with the sampling distribution of sample means and whatnot. Okay, the check your understanding talks about human pregnancies, and the birth varies according to a distribution that is approximately normal. That is very important to us. We have a mean of 266, the standard deviation is 16, right? So we have X distributed normally with mean 266 and sigma 16. Okay, find the probability that a randomly chosen pregnant woman has a pregnancy that lasts for more than 270 days. So A randomly chosen, this is the probability that X is greater than 270. Right? If we compute the z-score, right, not too hard to set up the computation for the z-score. Okay, we know that the z-score is going to be 270 minus 266 all over 16, right? So 270 minus 266 divided by 16, that is 0.25. So we're looking then for the probability that z is greater than 0.25, which will be 1 minus the probability that z is less than 0.25. Right, let me slide that over so you can see. So, distribution, normal CDF, 0.25, we set that up, right, 1 minus that number, and we get that that probability is approximately 0.4013. Alright, so in other words, about 40% of women have a pregnancy that lasts longer than 270 days. How much is 270 days? And that's about 9 months. Okay? Now, suppose that we took a simple random sample of 6 pregnant women. So that would be n equals 6. Let x bar represent the mean pregnancy for the sample. What's the mean of the distribution? Right? Well, the mean, right, mu of x bar is simply mu of x, which is 266. Okay. What is the standard deviation of the sampling distribution of x bar? Sigma of x bar is going to be sigma of x divided by the square root of n. Right? And if I do that, that's going to be 16 divided by root 6. Let's go ahead and give that to 2 decimal places. So we come over here as 16 divided by the square root of 6, and that is about 6.53. Okay? And check that the 10% condition is met. Right? So our sample size is 6, and we know that that is less than or equal to 10% of our population. Right? Why? Because n is certainly greater than 60. The population of pregnant women is a bit more than 60. Okay? Then finally, find the probability that the mean pregnancy length for the women in the sample exceeds 270 days. Okay? So here what we're saying is the probability that x bar, right, or the mu sub x bar rather, x bar, the probability that x bar is greater than 270. Alright, so we need to find the z-score for that one. Alright, and I'll call that z2 since it's another z-score. We'll come over here and label that z1. Alright, so z2 is going to be 270 minus 266 all over 16 divided by root 6. Right? And I'm going to use this exact rather than this rounded, because if you take a rounded answer and then round again, you tend to lose your accuracy. Alright, so we're going to come in here, right, and I have that answer, 6.53, right, so really what I'm looking for is 270 minus 266 divided by that number, right, and that is about 0.61. Okay, so that z-score is about 0.61. So now I'm saying, what's the probability that Z2 is greater than 0.61, which would be 1 minus the probability that Z2 is less than 0.61. Okay, and for this piece, right, do that in our handy dandy calculadora. Right, come over here and we go second distribution, normal CDF, 0.61. Right, that number, 1 minus that, and so we get 0.2709. Right, so that would be about 0.2709. So what does this tell us? This tells us that if we take any single pregnant woman, we find out that there's about a 40% chance that they have a pregnancy that's longer than 9 months. But if we were to take just a group of 6, then there's only a 27% chance that their pregnancy averagely is more than 9 months. Okay? Very important, the notation, and in fact, right, one of the things that is good practice, right, X bar is normally distributed, right, with our mu that is the same as mu sub x and our sigma sub x divided by the square root n as a standard deviation. Okay. Now, why can we say X bar is approximately normal? Because our initial population was approximately normal. So even though we have a small sample size, initially we're approximately normal. That's going to help us out. Okay? Why? Because if we look at this next piece, the normal or the large sample condition for sample means that if we're approximately normal, then so is the sampling distribution. Okay? This is true no matter the sample size, if the population distribution is normal. However, if the population distribution is not normal, then we can use the central limit theorem, which tells us that the sampling distribution of X bar, right, this is read as X bar, right, that the sampling distribution of X bar will be approximately normal in most cases. In most cases, if n is greater than or equal to 30. Okay? Sometimes n is 10 is good enough. Sometimes n is 100 is too small. So be aware that the central limit theorem does tell you and does not tell you. Basically it says, hey, if our sample size gets large enough, then our sample distribution of sample means is approximately normal. Alright? So the sample distribution of the sample means is approximately normal with some mu sub x and sigma sub x all over root n, as long as n is sufficiently large. Purposely vague language, important that you understand the vagueness and the implications.